Welcome everybody. The pace at which people are joining is slowing down. You never know, of course, when the last person is in, but I think we should get started and don't let those of you who are already here wait any longer. So my name is Ger Koole. Welcome to this webinar. Please note that this meeting is recorded. So if you say something that's part of the recording, we'll publish this webinar, and also our other webinars are on our website, so you can always look it back. But please note that if you say something, then that's part of the recording. So welcome again. Glad to see you all. What's today's subject? Well, you all saw the title and you see it again here. So what we're going to do today is a bit more theoretical subject. Actually, from the next couple of webinars will be way more practical on scheduling. But this is, perhaps the summer is the right time to, perhaps you have some time to dive into some more theoretical subjects that are not directly related to your everyday work. So this is, perhaps part of that. So a bit more theoretical subject, and I hope to make you clear that it's really the fundament of many of the things we do in workforce management, and that it's I think useful to learn about that. And I hope that by the end of this webinar, or you agree on that. And it's something that I called Poisson Noise, and I will explain why I call it noise later on. But why is it called the Poisson noise, or the Poisson distribution, or Poisson process? It's because of the person who I don't know, invented it or found it. I think it's mathematics, but it's a phenomena you see often happening. And this French mathematician, he was called Siméon Denis Poisson. He was the first to come up with it, so it's named after him. So what are we going to do? I'm going to show you what it is. What are the consequences? Of course, not a lot of detail. This webinar takes 30-35 minutes. So, but I hope to give you an impression of what the consequences are for forecasting and scheduling. And then there are some, these consequences are I guess to a certain extent negative. So how can we avoid this disadvantage? So that's what we're going to talk about today. So let's get started. The first thing what we're going to do is what is actually this Poisson noise? Yeah, and to say it in a few words, and I'm going to give you a bit more feeling for it, but to say it in one short phrase, it is the extent to which calls, the number of calls, the volume, fluctuate around the forecast you make. Yeah, suppose that you make a forecast, and a really good forecast, then, and I will say why that is the case, you will still see fluctuations around that forecast. So, to give an example, suppose you have a certain quarter of an hour and you have a forecast that is 75 for this 15-minute period. So, how many calls will arrive? Of course, it's a 50-minute period. So if you look at one particular minute, how many calls would arrive in one particular minute? Of course, 75 divided by 15 is 5. So a first guess would be 5 calls. Yes, but is it always, and assume that you have a really good forecast, is it really exactly 5? Yes, and that is the main thing, the main underlying question that we're going to answer. And I want to show that to you. Yeah, so I want to go have a look at these 75 calls and see how many calls actually arrive. And to do so, we go to Excel. So I'm going to stop PowerPoint here, and show you a blank Excel sheet. So let me go here. So yeah. So here you see in Excel. So now I'm going to look in the A column. I'm going to make one particular. I'm going to look at one particular minute. Yeah. So that is, let's say, the first minute of this quarter. So you expect 75 calls, but it's not the case that these 75 people that are going to call you, we assume for the moment, you can also apply to other types, but let's say incoming calls. So these 75 people that are perhaps unaware that they are going to call that quarter, but who are going to call that quarter, they do not coordinate. Okay, if you call the first minute, then I call the second minute. Yes? So every one of them randomly chooses any of these 15 minutes. Yes? Okay, so 75 times, the first minute 75 times, each of these customers, say, throws a coin, of course, not a fair coin, but a bias coin, to decide, and really not explicitly, of course, but that's something that goes on in your head without you being aware of it. Yes, perhaps you were when you call exactly. But so there's a probability of 1/15 that any of these 75 customers calls in this first minute. Okay, so let's mimic that. Let's simulate that in Excel. And that's why I opened Excel. So what am I going to do? Well, I don't know if you are aware of it, but in Excel, there are all kinds of functions that are useful for random numbers. Let me make this a little bit bigger for you. So what I did here, I did a function rand, and that gives me a random number between 0 and 1. Okay. So how can I use that to simulate, to mimic these arrivals of these 75 people? Well, as I said, let's say the first of these 75 takes the first interval with probability 1/15. So if this random number between 0 and 1, if that's smaller than 1/15, that happens in 1 out of 15 cases, then I assume this customer is arriving the first minute. Yes. Okay, so now by doing this, this rand, some random number, if that is below 1/15, then there's an arrival of the first customer. I do this for all my 75 customers for the forecasted number of arrivals. And as you can see, there are some zeros and ones. Yes. And what I can do now, if I want to know how many of these come during this first minute, of course, I can take this sum over these 75 people. And then I see that not 5, but 4 of them arrive. And I can repeat that 4, and let me make it a bit more visual by hiding some of these columns to get everything in one, like this, for example. Oops, still not enough. So I'm hiding some of the rows to show everything. So now, actually, every time I do something in Excel, it recalculates and gives a different number. Again, not 5, but 3. So let's make a number of copies. 15, 2, 3, 4, 6, 8, 10. Let's say around, this is around 15 columns, doesn't matter. Actually, if you are a mathematician, then you might say, hey, you should, now it can happen that a customer arrives twice, so, but let's not make it more complicated. I think this really shows what's going on. So the first minute, there are 6 arrivals. The second minute, there are 4 arrivals. The third, there are 2 arrivals, etc. Yeah, so what you see is actually, it's 75 calls over 50 minutes, approximately, actually. But the number from interval to interval varies. And let's put it in a small graph to make it even clearer. Oops, it's thinking. Yeah. So here you see, oh, I actually took 13 minutes instead of 15, but you see that the number of arrivals fluctuates quite a lot. Yes. So that is actually Poisson noise. And if you would quantify there are some mathematical laws underlying this variability that you see here. And these laws, and we won't go into the details, then you really have to, well, follow a lecture on mathematics. By the way, there's lots of details on Wikipedia on this. So if you're interested, you could have a look over there as well. But the laws of this variability, they are indeed described by Poisson and written in this in certain mathematical formulas formulated by Poisson. Okay, let's return to the. So I hope you are convinced that there is this variability, and I hope that by doing this small demo that I showed you where this variability comes from. Okay, let's go back to the presentation. So, by the way, I didn't do it, but if you take the average over a number of minutes, yes, then you get this, you get 5 or very close to 5. That is actually why I called it noise, because noise, and sometimes people call it white noise, but noise is something that, well, there's no signal in it. It fluctuates around the value, but there's nothing to learn from it. Yeah? So therefore, I have had white noise, then the average is 0. So what I mean by that is that it is randomness without explanation around this average value, which is 5 per minute in this particular interval. And again, Poisson was the first to formulate the laws underlying these numbers. How often, if the average is 5, how often does 4 occur? How often does 3 occur? There are mathematical formulas for that. And if you would do a simulation, just as I have done, you could empirically, just by experimenting, you can reproduce these values. And actually, talking about Wikipedia, this Poisson distribution, it is there in the arrivals of calls in a call center and in the arrivals of emails and chat requests, etc., etc. But it is everywhere around us. Yeah, it's not just unique to call centers, not at all. Of course, in the time of Poisson, the telephony was not yet invented. There were no call centers. He actually studied the number of arrivals that arrived at certain ports in Paris. Yes. So here on Wikipedia, again, there are lots of information on Wikipedia on these type of subjects. Here are some examples. Yes, the number of meteorites that strike the Earth every year. All kinds of the high and low numbers in XM. Yes. Defects. Sometimes you think, oh, my car broke down again. It is because it's getting old or something. Of course, then the average goes up, but it might also be Poisson noise, just randomness. Yes, things do not. If your car break down once a year, then there is no memory in the car that says, okay, now it's 365 days ago. Now I break down. No, that's a random process, and sometimes these random events are clustered, and then you think, oh, there's my car there's something wrong all the time. This is also a funny example. Also, I just a screenshot from Wikipedia. The number of chewing gums on the tiles in the sidewalk. Yes, so completely random process, and again, They not all the tiles have exactly the same number of chewing gums. Yes, that's also a Poisson process. And actually, what I just saw, people often see a signal, see something in, well, it's just noise. Yes, here at CCmath, we also sometimes try to see something. If we have more or less customer or customer requests during a certain month, then you start thinking, what are we doing wrong in our marketing or something? But it can also be completely random. Of course, it can also be seasonality. In the summer, usually things are a bit more quiet. So talking about forecasting is about what is seasonality, what is noise, making this distinction. And because of the noise, that makes it harder. If there's no noise, then you know for sure, okay, it is seasonality. Yes, and that's exactly this point. So this noise makes some of the steps in workforce management more difficult. By the way, if you're interested in noise in general, not focused on call centers, there is this, well, it's a thick book, so it's a long read, but it's quite an interesting book. There's a book about noise in general, in all kinds of processes, in justice, how judges introduce noise in their sentences, how doctors see signals that aren't there, etc., etc. Interesting book. Well, it's still holiday time, a good moment to read some books. So, but you should take a few weeks because it's really a thick book. Kahneman, by the way, he was a Nobel Prize winner. I think he died last year, but he wrote some more interesting book. But well, in this context, I really like this one. Okay, so I hope I made it clear what Poisson noise is. And now let's do the next step. What are the consequences for forecasting? Shortly, of course, no time to go into lots of details, but just to give a flavor just about this Poisson noise. Also, what are the consequences for safety staffing in the context of the Erlang formulas? And then, of course, knowing that it makes things more difficult, this noise, how can we, mitigate the negative effects? So first about forecasting. So the risk of noise is that you think it's a signal and that you think, hey, that you make it part of your forecast. So you project today's or yesterday's noise onto the future. And that is, of course, that's really wrong. And people call that nowadays, call that overfitting. Yeah? So then you see something and your model is really completely adapted to the history, to your historical data, but it's not going to reproduce. So that's what we call overfitting. So how do we avoid overfitting? Well, the answer looks simple, but to make it really work is quite difficult. But you should average in the right way. Yes, and why? Well, here is a theorem and a very specific one. In mathematics, we formulate and we try to be as general as possible. This is super specific, but it's something that having the things that Poisson invented and others, you can really prove it. So suppose you have two, what we call time series. Yes, just a number of arrivals over minutes or over days, whatever. Yes, just numbers over time. Yes. Now, if you have two similar time series, with the same average, but also, well, there are some technicalities required, but let's forget about that. So two similar time series, yes, and you take the average of them, then actually the noise is reduced. Yes, and it is reduced with a factor of the square root of 2. What is the square root of 2? I guess you all know it, but the easiest way to think of the square root of 2 is the length of this side of this triangle. Yes, it's of course Pythagoras who tells you this. There's this nice picture that I copied from Wikipedia. But so it's around 1.4. So that means that that is by which it's reduced. And here I have two series, the orange and the blue one. Just noise, yes, and I took the average, the gray one. Of course, the gray one is always in the middle, and because of that, you can understand that there is less variability in the gray one. And actually, there is one, if you look at the variability, indeed, you divide by 1.4, sorry. For those of you who know a little bit about statistics, again, the average here is 10. The standard deviation of this Poisson series is the square root of that is 3.16. And then you divide by 1.41, you get the standard deviation of the average. By the way, this is not difficult to reproduce in Excel. Yes, you can, of course, easily take an average, reproduce the numbers the way I just described, and take the average and calculate the standard deviation. Yeah, and of course, if you're not familiar with the statistics behind that, this is just for those of you who are. Yes, so averaging in the right way is important. Yes, and there are certain methods that do that better than others. One of the methods that doesn't do averaging right, for example, is a method that's often used, is Holt-Winters, but it gives a lot of weight to the last numbers. So there's a lot of overfitting with respect to the last numbers. That's one of the reasons why Holt-Winters is not very appropriate. But again, also that if you're not familiar with these particular methods, no problem. Okay, so that's for forecasting. Let's talk about safety staffing. I'm sorry. Let's look again at this forecast of 5 per minute. Yes? And now let's assume that we're going to decide how many agents we need. And so I see some questions coming by in the chat. Perhaps Jesper of CCmath, who's also in this call, can answer this. And otherwise, I'll take them in the end. The average handle is suppose that these calls have an average handling time of 5 minutes. Yes. Now there are different ways to calculate load. Perhaps you're familiar with the total minutes that of agent time that you need. Then you might multiply the 75 calls times the 5 minutes. Then you know how many agents minutes you need during this quarter. But when it comes to the Erlang formulas, it's always very instructive to use the same unit of time for everything. Yeah, so we saw that the 75 calls that arrived during this 50-minute period, and that's of course the same as 5 calls on average per minute. On average, we saw the fluctuations. The average handling time is 5 minutes. There's also variability in that, but let's not dive into the details. So if you multiply them, you get something which is the offered load, which is of course 5 times 5 is 25 here. And this is per minute, and this is in minute. So actually, this is, there's no dimension. Yes, there's per minute times minute is nothing. And in telecom, we call this Erlang. If you look up again on Wikipedia Erlang, then you get, of course, the Erlang formulas, but you get also a dimension in telecom, and that is, well, just a name for something which has no dimension. Yeah, but the story is, if you have 5 calls per minute, an average handling time of 5 minutes, then on average, 25 agents are full-time busy. Okay, but how many agents would you schedule? Yes. I don't know if anybody has a suggestion. You can put it in the chat. I'll wait a couple of seconds. So the forecast is 5 calls per minute. The average handling time is 5 minutes. How many agents would you schedule? Anybody a suggestion? You all realize this is recorded, so perhaps you do not dare to put a number. 28. Yeah, that makes sense. More than 25 because of the noise. Exactly. Yeah. And then after SKG, Yeah, what budget allows. Okay. Yeah, but what happens if you schedule 25 or less? It depends on the KPIs. Yes. Good answers. Yeah, makes all sense. But you typically 25 times square root of 2. Okay. We'll get to that. That is an interesting one. How many agents would you schedule? Well, what I did here, I made this plot. And what is this plot? This is actually the shrinkage. Well, okay, interesting. We're talking about shrinkage. There's a difference between safety staffing and shrinkage. Again, we cannot go in all the details, but here I'm talking about the number of agents which we call the net workforce. No shrinkage yet. These are people that we're scheduling here that are full-time available to take calls. On top of that, they have shrinkage, planned shrinkage, unplanned shrinkage. Yes, but here I'm talking about after the safety staffing, then you have to add the shrinkage. Yes. So that's a good remark. That you really have to take that into account. What you see here is the workload from minute to minute, just randomly taken. So that fluctuates, of course, because of the number of calls that arrive every minute. And then after 5 minutes, also some variability here. Let's not go into the details. Then the decrease. So here there was a service ended. This kind of assumes that you have lots of agents. So there's no waiting. This is just the workload if you could work it away immediately. Yes. You see there's quite some fluctuations. The workload, the average workload, is at 25. So here at this dotted line. And you see, of course, that sometimes less than 25, if you would schedule 25 agents, which is exactly to this offered load, then sometimes here you have idle agents, but sometimes here a little bit and here a lot, you don't have enough agents to handle the work. So this work here gets delayed here a little bit and perhaps here. Yes. And so typically what happens if you schedule the number of agents equal to your workforce, then, well, there is a lot of delay. So typically you want to schedule a bit on top of the offered load, and that is what we call the safety staffing. So that is the staffing you need to account for the fluctuations. Yes. And so in this case, and again, that depends on your KPIs. I think if you do 80-20 here, this is what I just said. So if you want 80-20 here, and if you, well, depends on your Erlang model, whether you have patience in it, you might come at 30. Yes. So that really depends on your KPIs and also how quickly calls abandon. Yeah. So indeed, Erlang X, if you assume that on average people abandon the queue after 5 minutes of waiting, then you need 30 agents. But of course, if you change that, you might get to 28 or 29, some of numbers that were suggested. Yeah, so really, so Erlang himself, who made the Erlang C formula, he started with the Poisson distribution, and that is part of his mathematical calculations of his, and that's implicit in the formula, in the Erlang C formula, and other formulas like Erlang X. They also built on these Poisson models. Yes. So what happens here is that the Erlang formulas tell you how you have to deal with this Poisson noise. Okay. And then we go to the final step, and that is, okay, we know we have this Poisson noise. We saw how we could deal with it, but perhaps we're not happy with the fact that we schedule 30 agents, while on average, we know that 5 agents are idle. Yes, but we need these idle agents to be able to handle to be able to handle the offered load within within your service level agreement. Okay, so what are the things we can do to avoid the bad effects? So the first thing, of course, is that we talked about forecasting and staffing, is that you have to make sure that if you do the overstaffing, if you apply the Erlang formulas, that at least your agents are sitting there at the right moment. Yes, and if you have a bad forecast, then typically at certain moments you're understaffed, and at other moments your overstaffing is too high. Yeah? So a good forecast makes sure that you always have the right amount of overstaffing. Yeah? So that is the first thing. Yeah? So making sure with a good forecast and filtering out the noise in the right way, if you want to, that's a way to put it. That is the first step. And again, I mentioned it. There are certain methods which are, of course, more appropriate for filtering out this noise than others. If you want to reduce the overstaffing, yes. If you want to, I see a remark, set occupancy targets in your calculation, perhaps. Well, you can set occupancy targets, but that might mean that you don't meet your service level. Yes, sometimes in certain situations, you might have an occupancy target and a service level target, and then sometimes your occupancy gets too high because you have organized things in a good way, and of course then you might look at the occupancy targets. But typically, what I think is it's good to look at both. But let's talk about the overstaffing. And to reduce overstaffing, well, it's again about, it depends on the size. The bigger, and that's exactly what we're going to talk about is about size. Okay, so how to reduce the overstaffing? Well, it's again about everything. We're focusing on this Poisson distribution, on this Poisson noise, and again, we saw we can reduce the noise by averaging. So one thing of averaging is we saw these fluctuations a few slides back in the load. Now, of course, if you are allowed to compensate a period with a high load with a period way later with a low load, of course, then you can do with less overstaffing. Now, you can say, okay, instead of 80-20, I do 80-30 or 80% within 1 minute. Of course, that makes a small difference, but a very small one. It's much better if somehow, instead of having to answer in 20 seconds, you can answer in 20 minutes or in 20 hours. Now, how can you do that? Well, ways to do that is, instead of stimulating your customers to send an email, and then typically your time to answer is not 20 seconds, but perhaps 1 business day, or sometimes even a few business days. What I also see, and I saw some interesting implementation of that in hospitals, where you typically have a small size and it's very hard to meet your service level, is that you allow for callbacks. So people have the options, or sometimes it's not even an option, but people have the option. Okay, the waiting time is long. If you want, we can call you back at a certain point in time, or within a certain point in time. And then people are called back, and that feels way better than having to wait 20 minutes on the line. So that is over time, averaging over time. Another way to average is, it's not really averaging, it's by summing skills. Yes. So again, a theorem, and again, there's a square root here. So, and this phrase is a bit Well, it's about the noise of the sum and the sum of the noise, and the difference of that. Of course, you can take these lines separately, and they both have a certain amount of noise, quantified by the standard deviation. You can sum them up. But you can also first sum the arrivals and then look at the noise. Now, you would normally think in which order I sum thing, it doesn't matter. Yeah, but when it comes to noise, to variability, that does matter. Yeah, and the noise of the sum is smaller than the sum of the noises. I'm going to illustrate that. And here it's quantified again. If you have two similar lines, two similar time series, yeah, then the noise of the sum is the square root times the sum of the noises. Yeah, so it's less. Yeah, so if you have the noise of one line, the noise of another line, you sum them. If they are similar, it's twice the noise of one of these lines. Yes, but if you sum them first, then it doesn't double. It's, well, 1 times 4 instead of 2 times the noise. So that then you have less noise, and if you have less noise, you need less safety stuff. So let's take an example here. Here again, you see the two lines with the average of 5 to 10 here again, and then you have this sum. Now, of course, you do not see that easily, but the variability of the sum is less than the sum of the variability of the orange and the blue one. By the way, if you look at the sum, you almost say, hey, there's some seasonality. This must be weekly data. On day 3, there is less volume. Here, there's less volume. Here, there's less volume. But I can tell you, I make these numbers up. There's no seasonality whatsoever. This is not weekly data. Yeah, so at least I saw a signal here that is really not there. So, but that's a small short aside. So what's the message here? Standard deviation of the Poisson series is 3.1. So if you double them, you get to 6.3. And if you look at the standard deviation of the sum, 4.5. Yes, so considerably less. So let's translate that to staffing. And now one of the remarks has somebody who already introduced the square root of 2 in the staffing. It's a little bit different, but you're close. So the theorem in words is that the noise of the sum is less than the sum of the noises. And here is a theorem, and actually in mathematics, without going into any details, there's a lot of theory, and that introduced an alternative to the Erlang formulas, and it's called square root staffing. Yes, again, the square root. And translated to our example, it says that the safety staffing of the sum of two similar time series is smaller than the sum of the safety staffings with a factor of, again, square root of 2. So let's apply it to an example. Perhaps this is a bit abstract, but let's apply it. So we go back to example. Yeah, we had a queue with an offered load of 25, and we needed 5 agent safety stuff. And we needed 30 agents in total. So 25 is like the base load needed to deal with the offered load. And then you need 5 additional agent safety stuff. So we have 2 of these queues. So if they are separate, we need 68. Now we're going to put them together. Of course, we still need to deal with this base load of, well, 2 times 25, 50 agents. But now we have the safety staffing, but that is now a factor square root of 2 smaller than when they are separately. So it is 2 times 5, but now divided by the square root of 2, and then you get to around 7 agents. Yeah. So in total, you need 57 agents, so that's 3 less. So that is around 5% savings. Yeah, so you need, by adding them and by using this principle, of course, you can check it using the Erlang formulas. You will find very similar numbers, but you see how, again, from these basic principles of Poisson distribution, this follows. And of course, again, without going into all the details about multi-skilledness and skill-based routing and everything, Here you had two separate queues, and there was a reason why you had two separate queues, because these agents probably have very different skills. Now, putting them together in one queue means that all the agents should have both skills, which means a lot of training, which is perhaps impossible for all kinds of reasons. But if you dive into, well, the mechanisms behind skill-based routing, and then you realize that in general, you do not need all the agents to be multi-skilled, a certain fraction of it. And the other agents can still be single-skilled. One or two webinars back, we talked about this multi-skilled, about skill-based routing and how to do safety staffing in such a situation. Okay, we're getting towards the end of the webinar. So, well, I hope that, well, the message I want to, I mean, I really think it's useful to know about these things like variability, to have an understanding of this Poisson distribution, to understand how this translates into overstaffing. It is the reason why we need overstaffing, but it's also used in calculations to really quantify this overstaffing, this safety stuff. So I hope that you agree that, well, by looking at things this way, that you get a better understanding of what's happening in a call center. And really, I hope also that this message that sometimes, that often actually we see signals where there is noise, that's really the case. I see it a lot of times happening in real-time management, that people react to things that disappear themselves because it's just random noise. So I hope that you agree with that, and that you enjoyed listening to this webinar. To wrap up, these type of things, we present them in our trainings. So if you got interested and you want to learn more, then please follow one of our training programs. So we have all the subjects we mentioned and much more are part of our trainings. We have different options for the trainings. We have e-learning, where you can do it at your own pace, at your own time. We give online trainings. We give face-to-face trainings. We do it in-house or with a group of people that register independently. We can have definitely the in-house trainings. We can do them online, or we can come to your favorite location. If you want to know more, go to our website or contact one of us. And if you're interested to see how we deal, because our bread and butter is really making software, if you're interested to see how we deal with the noise in our software products, please let us know. We're very happy to give a demo, or just to have a chat if you have certain challenges with related to noise or something else in WFM. Bas is also in this call. Either Bas or me or together, we're very happy to book a 1-hour slot and to see how we can perhaps help you with your WFM challenges. As I said in the beginning, our next webinar is on our new version of CC Schedule that has a super interface that really makes work a lot easier, has a super engine under the hood. And we're going to tell you a bit about the ideas behind that. So way more practical. That's in 1.5 months. So you'll get an announcement, of course, but I hope you'll be there as well. And right now, I would like to thank you for your attention. Great that you were here despite the holiday season. I hope that you find it instructive. If you have any feedback or whatever, please contact us. And I think we already answered some of the questions, but perhaps some of the questions remain unanswered. So let's have a look at them. But if you want to leave, do not hesitate. And again, we'll put the recording in a few days. It will be on our website. So if you want to look back at what we discussed today, please go to our website in a few days. So thanks again for your attention. And let's have a look back at what is in the chat. What is the birth and death rate in the Poisson noise? So if you talk about birth and death rates, and then you talk about birth and death processes, and that's a technical concept, but that's underlying the Erlang C calculation. Yeah, actually, the birth rate is the the forecast actually. Yes. But then you really have to dive into this whole technical subject of Markov processes. Yes, but that is after the Poisson distribution, the next step in understanding the Erlang noise. Okay, yeah, I see some people enjoyed it. Thanks a lot for your nice words. Yeah, what do I mean by similar series? I mean that the volume is similar, but that is there's also an additional condition that that's a technical condition that they are independent. Yes, but that is a technical condition. But two Poisson series with the same average. That's what I mean by similar. You can generalize everything I said to, of course, different volumes. Typically, if you have two lines where you have multi-skilled agents, it's coincidental if the volumes are the same. But today, just for simplicity, I took same volume, but had the same idea that you use the Pythagoras, that you have this side in the triangle. That is that same rule applies. Okay, do I miss any of the questions? You're welcome. I don't think so. A book to learn about time series forecasting. Well, to be honest, of course, perhaps I should have mentioned that. There's my book. I have this book, Call Center Optimization. And there is, so I think that's one of the few books out there. There's, of course, a lot of scientific literature on forecasting. There are also scientists who looked at call centers. But to be honest, that's all very technical. So you need a lot of background, and it doesn't always answer the questions you might be interested in. So there are some... Rob Heinzman, for example, has a nice book on forecasting, but it's way general, which is also free. You can consult it online. You can also buy a copy, but hard copy. But it's there. If you want to look for what is really relevant to call centers, then you really have to need a lot of background and a lot of knowledge. So that is a problem with lots of the scientific literature. In general, call center forecasting is really different. There are certain issues in call center forecasting that are not part of, let's say, the general body of statistics and forecasting. So I think that you really have to understand both the statistics and call centers very well to be able to do a good job. Yes, and again, few books deal with that. I try to do that with my call center book. But again, I really do not know of other books that do something similar. Okay, I think I answered all the questions, and I see no more questions coming in. So if you have, thank you, Gaetano. It was a pleasure. well, good to see you again. As I said, lots of known faces, but also other people. So if you were here for the first time, I hope you enjoyed it, and I hope to see many of you back at the next occasion. For now, thanks again, and then we're going to end the recording and close the session. And again, if you have any questions remaining, you can always contact us, and we'll be happy to answer any questions or go into discussions, depending on your needs and challenges. So again, thanks a lot. And see you at some other occasion. Bye-bye.